Hey, what's going on YouTube? What's up? Today we are going to be doing our first ever Bonanza. This is going to be fun. I hope you enjoy this. Why isn't this working? Oh no. iPad, vertical. I thought I had everything set up correctly. Oh no. Dang it. Really? Still? Okay, well, we're going to do our first ever Bonanza. This will be fun, y'all. Over the last few days, we've been doing linear algebra here, live, practicing problems, teaching math, getting questions, answering questions. If it's your first time here, my name is John. I am a former mathematician turned software engineer, ex-Google, blah, 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 who cares? I'm bringing back my passion and love for mathematics and sharing it with you all. So this is going to be fun. We're going to try to grow this stream from 0 to 1,000 as quickly as we possibly can. So hit the subscribe button, hit the like button, leave comments below, y'all. We've already hit 120 subscribers in like 11 days, which is insane. Compared to my last channel, that's insane. So, I feel good about the growth so far. I think that there's some demand out there. There's some people who've reached out. I chatted with somebody over Zoom, but nobody's commenting publicly. Come on, let's start up a math discussion in the chat, in the chat and in the comment section. So, if you leave any comments or questions, I can respond to those at the beginning of these videos before we jump into the live math practice section. Hey, Math Spellbook, good to see you, man. How are you? Math is popping up. Yeah, we're gonna get math trending over here. Math is gonna be, we're gonna try to make math as fun as it can be. So, that reminds me, somebody did give me feedback like, oh, the math hobbyist, that name sounds like you're not an expert. You don't know what you're talking about. I do know what I'm talking about. I'm just rusty, okay? So I am a former mathematician, but I'm just rusty as heck. I've been working in software for a while, and I'm just bringing it back at the moment. But I still call myself a hobbyist because I'm doing it for fun. Like, I am literally doing it for fun. I know that I'm not going to get a single dollar from ads from YouTube because ad money doesn't exist through YouTube, basically. But who knows? Maybe I'll get some private tutoring students, but the type of math that we're going to be working on here is for fun. I doubt I'm going to get any abstract algebra students, although that would be sick. That would be great if so. Cool. Great to see you in such a positive vibe always, man. Today's going to be our first ever Bonanza, which I'm stoked about. Bonanza number 1. Yeah, being a generalist is where it is at. No shame. Yeah, I think it's a great hobby to have. Just learning as a hobby is really, really fun. One thing, I meant to rewrite this in. I first wrote the word bonanza with an H, and I was like, is that even a real word? And I looked it up, and yes, it is a real word if you remove the H. And it just means a synonym for extravaganza. It's just another way to say extravaganza. But what's cool to me is that, for whatever reason, Bonanza with an H, that is a famous board game. And it's about trading beans. It's kind of like Settlers of Catan, but it's a card game, and you're trading beans with each other. It's a German-style board game, and German games are weird as heck. The themes are always super dry and strange, like we're bean farmers. But yeah, I'm very excited for that game. It's coming in the mail. So I thought that would be funny. Board games are kind of really closely related to math, honestly. Like, it's a little self-contained logical system with more flavor and more fun around it, but it's still logic. It's still like a logic game. So to me, you might be like me, you might find math like a game. I certainly do. So that's what we're going to do today. We're going to play a game together. And I've got a bunch of free time today, so it's going to be a long stream. We're going to be doing several exercises and looking at some theory. And I wanted to say that next week, we're definitely going to move on to calculus and a little bit of analysis, which is fancy calculus. And then the following week, we might cycle back to number theory. So we did 3 videos on number theory. Now this is going to be several in a row of linear algebra. Next week, 7 in a row of calculus, and then back to number theory. That's what I'm thinking. I never knew about that board game. Yeah, it's really cool. It's super cool. Yeah, we will get into abstract algebra. We might touch on a little tiny bit of abstract algebra today, which I think would be fun. I'm trying to mix in the different styles of math, and that's something that I think is somewhere where this stream and this idea can shine. Like, it's not a math course that's going through one textbook. I can compare and contrast. Here's what this person calls this idea. Here's what this person calls this idea. Like, here's the different ways to write down the same idea. And we did that a little bit yesterday. So I thought that was pretty sick. Math is of patterns within reality, interestingly enough. Yeah, I tutor a couple of little kids, and I tell them that math is, in a sense, all about finding patterns. So that's really fun. I think it's not untrue at all. Math is all about studying patterns. Patterns in numbers, patterns in logic, patterns in arguments, patterns in whatever. Okay, so this is going to be fun. I wanted to rework this problem. I'm making a little bit of progress thinking about it. I think I just... let's clean up. So I copied over the entire dang thing from yesterday's worksheet notebook thing. And so we have this weird unit cube, and it's asking what are the other 4 corners, and I'm pretty sure that this corner here is I minus j. I minus j. And I want to see why. I still want to understand why. Or it could be j minus I. No, I minus j. So I minus j. Yeah, what I'm trying to get at is I made the realization just when I was like copying this over. I made the realization that, oh, wait a minute. Okay, so the normal unit cube would have, like, the y-axis, the second coordinate, is along that diagonal because both I and j both have coordinate 1 in this, or value 1 in the second coordinate. So those are along the same line. And then if you take I and then subtract j, like, I still think 0, 0 is over there. So is it true? I'm just so bad at visualizing 3D space, y'all. I don't know why this problem is tripping me up so much. I think so, yeah. I think that makes sense. Like, they cross diagonally across this cube, and then this line, this dotted line, this red dotted line is like the x-axis, and the green one is the y-axis. So it's like the cube. It's like the regular, it's like this dang cube, but instead of being tilted like I imagined it the other day, instead it's like it's just rotated around. So I'd have a hard time drawing it, but it's just like shifted. Something like this, I think. So like you put the dice on the table and then you spin it just a little bit. Yeah, what is the question? Okay, so the question, it's super messy because of all the work from yesterday. Let me just erase a couple of things just to clean up. 4 corners of this unit cube are 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. So, I'm very convinced that the point where those vectors meet is 0, 0, 0. Like, because the only way to get the 0 element is 0 times each vector. So that is where all three of those vectors meet. The vectors are these blue ones. So sorry, this is really for... I mean, this is really best if you've seen the prior... If you've seen the problem before. I got stuck on this one, and I was like, I'm confused. I have a hard time visualizing 3D space. Yeah, and I was pretty confident that this corner in the bottom right here is I minus j. It does say that, oh, yeah. It told us that one of the corners is 0, 0, 0, which I already marked. One of them is 1, 0, 0. One of them is 0, 1, 0. And one of them is 0, 0, 1. So it already marked this one, this k equals 0, 0, 1. It already marked 0, 1, 0 over here, this j vector on the right-hand side. And then it says one of them is 1, 0, 0, and it didn't, and the diagram had this written in, I equals 1, 1, 0. Whoops. So the hint said that one of them should be 1, 0, 0. This blue coordinate, and I saw, well, 1, 0, 0 is definitely going to be I minus j, the two vectors that had been drawn, I minus j. So I had a hard time visualizing why that red corner would be I minus j. But now I think I see it because of how, like, if those are the x and y axes, I don't freaking know. I don't care. I'm pretty confident that I've marked these all correctly now, and I just want to move on. It doesn't matter. You can solve that a little bit more carefully for yourself if you want to. This is good enough. I've convinced myself, as I thought, that one corner is the right one. Let's move on. I'm tired of that problem. Yeah, so let's see. I hope I can keep up with you. Oh, analysis. Even though analysis is something I really want to learn, but I still need to practice the basic proofwriting. Yeah, we're going to have to do some proof writing if we're going to do any amount of analysis. And so I'll try to teach a little bit of proofwriting in the middle of that. It's not a tough problem. It's just boring. It was a boring problem, so I'm kind of bored of it, and I just want to move on. But it was weird. Like, I just have a hard time visualizing 3D space, and like if things aren't in the standard coordinate system, I don't know. Maybe I'm just rusty. Who cares? Let's move on. Okay, so I wanted to review a little bit about what linear algebra is. Linear algebra, it sounds super easy. It is about lines, and it's algebra, and like, what the hell? Didn't I study algebra in high school? Yes, you did. You even studied the basics of linear algebra. You studied the beginnings of a bigger theory, a bigger field of math called linear algebra. Pretty much everybody sees this kind of problem solving a system of two equations. So if you have two lines, they might cross at a point. If you have two lines, they might never cross. They might be parallel. Or if you have two lines, they might be the same dang line. and they have infinitely many solutions. They might just be two ways to write down the same line. So these are three options, and we want to understand when is it, can we say exactly when they have one solution as opposed to infinitely many or no solutions. And so here's a fun little problem that I just pulled out of thin air. What if you had two YouTube channels, and one of them had 1,200 subscribers after 6 years, and then the second one has 100 subscribers after 10 days? So which situation do you all think this hypothetical person might be in? Will the second channel ever overtake the first? I think so. Can we see if that's true? And if so, can we try to predict when that would happen? Let me answer a couple questions. How do you know when to move on from a problem if you aren't solving it? Good question. Former me would have just kept bashing my head against the table until I got it. And I would have kept working on it because I didn't want to lose the homework points. I didn't want to lose those points on the homework set. Current me, I don't know. If it takes more than 10 minutes, I'm just going to circle it and come back to it tomorrow because I have no deadline. I have no exam. I get to just let problems marinate. It's a good idea. Like, basically, when you, if you get stuck on a problem and you're not feeling like you're making progress, put it aside, work on another problem, and then oftentimes when you're taking a shower, the solution pops into your head. That comes up at work all the time. Like, you're trying to figure out why this button isn't working or whatever, and then you can't figure it out. Then later on you're taking a shower, and now all of a sudden you know, like, oh, the button's not working. I know why. It's because blah, 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 I made this change last week or something. Like, that's just kind of general problem-solving skills. Like, go for a walk, do something else, try to work on another problem, do something else, and in the background of your mind, it's going to keep working on that problem on, like, a background thread until it'll just pop up. For some people, it pops up in a dream, which is really neat. But, yeah, just put it aside and keep moving on. Do more problems. Do another problem if you're stuck. And then, also, I do want to pause on this question because it's a good question. Like, when to pause on a problem? I would say, if I were to do a math degree again or any kind of science degree again, maybe a master's in computer science or a master's in math or whatever, don't just do problems maybe from your medium difficulty book. Maybe you're in a class and you're using a medium difficulty book. Don't only do problems from there. Also, every now and then, take a look at harder problems and take a look at easier problems. So if you get stuck on a problem from your book M and you're stuck, go solve something easier. Go improve your confidence. Yes, you know some of this material. You know you can solve the easier stuff at least. Go back and review problems from a prior chapter. And just practice them. Do them again. Do the same problem again just to get another repetition in. And that's going to help your problem-solving skills. Then when you come back to the medium book, then you might have some more perspective and be able to solve that problem. Yeah, so that's my thought. Thanks for the thoughtful explanation. Thanks for the thoughtful question. All right, so YouTube channels, you have two of them. First and second. First one has 1,200 after 6 years. Second has 100 subs after 10 days. When will the second overtake the first? Okay, if you're not a nerd, here's how you do it. if you're not a nerd, and somebody asks you this, you say that you're, okay, second channel's getting you 10 subs per day, right? And if you're making 10 subs per day and you want to hit 1,200 subscribers, then that's going to be 120 days. And at 120 days, I don't know, period. Like, 120 days, there's 30 days in a month if you're not a nerd, so that's about 4 months. So in about 4 months, you'll be at 1,200, and then the other channel is growing much more slowly, so just like a little bit more than 4 months is the answer. If you're not a nerd, that's the answer. This is called a back of napkin calculation. If somebody asks you this in an elevator, try to have an answer quickly, and then they'll say, wow, that's really cool, I'm going to subscribe. But if you are a nerd, or if you do have a piece of paper with you, you could write down this as a system of two linear equations. You could solve this in weeks if you wanted, or you could solve this in days. And you can use the types of equations like y minus y0 equals the slope times x minus x0. So then we have a couple of points, and yeah, I don't know. I don't care. Like, basically, you set up equations like this based on a couple of data points that you can come up with on your own. And you solve that for both different equations. So the second one, I think, clearly is like y equals rise over run, y'all. 1,200 over 6 times 52, which is 300 if you're not a nerd. That's so stupid. I'm an idiot. I'm so stupid. I should stop joking too much. And then, yeah, so you come up with that equation, and the x-intercept, or the y-intercept is 0 because you started at 0 subs. In this, remember that x is weeks, or time, and then y is subs. So then the second equation is going to be y minus maybe 100 equals the slope, which is, we gained 100 over 1 week. We're solving in weeks. X minus 6 times 52 here. Now you have two equations. You get them both into the y equals mx plus b form, and then you use one of two methods. You can do the substitution method, or you can do method 2, elimination. So substitution is going to be get one or both equations, like y equals some function of x, and then you plug it in to the second equation, and then you replace every y with x's, like some equation of x's, and then solve for x for some number. I'm going to use c to be like a constant. Like, you solve for a number, And then you go back and you plug that back into the original, or into that equation for y, and then you get y equals maybe C1 and C2. So that's a substitution method. Elimination is different. You subtract one equation from the other to eliminate a variable. And this is a much more generalizable approach that then you can use with matrices. Like if we're solving an equation like this, this is like the two equations, x plus 2y equals 3, and 4x plus 5y equals 6. To eliminate the variable x, we could subtract 4 copies of the first row from the second. So the second line, we're going to subtract 4x, and then we have 0x, and then 5y minus 8y is going to be negative 3y. 6 minus 12 is negative 6. And now we rewrite as x plus 2y equals 3, y equals 2. And then we subtract 2 copies of the second equation from the first. So that will eliminate the variable y, and then, so 3 minus 4 is going to be negative 1, y equals 2. And it looks like, from my made-up numbers, though, that's the solution. I say that it's more generalizable because it's way easier to write this without all the variables, like this. And it's the same dang steps. 4, 5, 6 equals. This system of equations is the same thing. We're just not using the variables x and y and equals. I'm doing the exact same steps. Subtract 4 copies of the first row. So 5 minus 8 is negative 3. 6 minus 12 is negative 6. And now we have, I can even do this in one step, y'all. All right, so second line we can write as 0, 1, 2. And then I'm going to subtract 2 copies of that line from the first. So 1 minus 2 times 0 is just 1. 2... Maybe I did this. Oh, wait. Oh, yeah. Okay. All right. 1, 2, 3, subtracting 2 copies of 0, 1, 2. So subtracting 2 copies of that, we get 0 there, and then 3 minus 4 is negative 1. And then voila, here is our solution. So you can see that this took way less space than writing all of this. And that's for only 2 variables. Maybe it's not a big deal and you can see, you can solve this one perfectly fine by hand. But if you have 200 variables, if you have 200 equations, it's way easier to write a giant square of numbers and do it this way. Like in, I'm going to say that this is method 3 matrices, but really it's the same thing as method 2 elimination. It's just a different way to write it down. Okay, so let me catch up with some chat. Cool. That is a tough problem. How do you know when to move on? Thanks for the thoughtful explanation. Fortunately, you're a nerd as well. Good. I want to collect all the nerds who want to just hang out and listen to some weird dude rant about math. I immediately thought of system of linear equations as soon as you posed the question. I haven't reviewed linear algebra in such a long time. Yeah, totally. Like, linear algebra this is the very beginning. You know, this is the motivation, and this is why linear algebra is so dang useful. Like, a lot of real world problems are find when these two lines cross, find when these two planes or hyperplanes or whatever cross. But then this is the beginning, and then there's a beautiful theory around this that forms that you can, where we're going to get a little bit more and more abstract over time. But this is the motivation, and it's important not to lose sight of that. Like, this is the motivation. This is really useful. This is why you can make a lot of money if you work at NVIDIA or OpenAI or something, and you want to help work on their data science and train their machine learning algorithms, because in some sense it's a lot of this. Like, find the solution of two lines. That is such an inaccurate, hand-wavy explanation of of AI, but you know what? It's not completely wrong. It's all good. I'm sure the non-nerds are laughing. That's good. That's a goal too. At least the non-nerds. I want this entire video and stream and concept, I want it to be accessible to everybody at the beginning, and then it's going to get more and more complex, and I'm going to lose people at some point, but I hope it's still enjoyable even if I lose you, and we get to harder and harder math. I posted your stream into the Math Streams channel on your Discord. Oh, heck yeah. Yeah, go for it. I totally forgot to announce it today, so thank you. Thanks for keeping an eye out for me. Thank you for that. Matrices kind of helps reduce the work. That is true. That is true. And you can program computers to be really good at multiplying and solving these blocks of numbers. That's what GPUs are. GPUs are matrix calculators. And it's because linear algebra is amazing at calculating things like rotations. If you go from if you have a video game dice and you want to spin it around in video game space, you use a matrix to do that rotation. So GPUs are matrix calculators that originally were called that because of graphics. But really, they're computers that are great at calculating matrix math. I'm sure that that's totally wrong too, but it's not completely wrong. Let's keep going. Yeah. Oh yeah. That is what GPUs do. That's why they are really useful. They're good at calculating matrices. And they're also good at... let's get a little more specific. If you have a humongous matrix with, a trillion rows or something, there's a lot of theory about how you can take a big chunk of this matrix and calculate it with another chunk of the matrix, and you can tell two different you can have two different processes running in parallel. Let's see. I can't ad-lib this part, but like you can tell the thing to calculate these in parallel at the same time as you're calculating this part with this part or something. You can I'm making this stuff up. I don't know exactly how this works, but this is called matrix factorization and diagonalization and parallel processing. So GPUs are great at calculating two numbers at the exact same time instead of one after another really fast, like literally parallel processing. And that is why they're good at calculating large matrices. It's because they've been optimized for calculating different segments of the matrix at the same time. I don't know. I'm making shit up. Let's go on. All right, so those are the only two things I actually prepared. So I'm going to write down in my exercises table. Yeah, we solved that one that was bothering us. Number 12, we solved it well enough. I wanted to come back to think about Shilov 114 again. So this is a little bit more of a theoretical problem. Sorry, not sorry, I suppose. Shilov. Shilov is scarier. Shilov 114. This was a cool problem. I'm just going to copy it because I'm lazy. I don't know where my book is. This is a cool problem. I want to figure this. I want to try to take a look at this again. I don't know if I'm going to be able to prove it. Yoink. Magic trick. Magic trick. Let's copy all this. We don't need all of it, but most of it. Let's come back here. And paste it. Remove this part. Okay, Shilov 1.4. Show that the n factor terms of a determinant of order n exactly half have a plus sign according to the definition of 1.3, while the other half have a minus sign. Okay. All right, so let's get some review, because I know that not everybody here knows what the heck I'm talking about. What is a determinant? What is definition 1.3? Definition. I think that this is the definition of the signs of the terms of a determinant. And I think I can state it on my own, but I wanted to write it verbatim. But I don't know where my book is, so I'm just going to write it again from my own. Hey, how's it going, folks? How do you think about tensor rank 2 in comparison? I don't know what it... I know tensors are like multilinear algebra, and they're like kind of like an extension of the idea of matrices. I never really fully understood them. I hope to understand them again now that I'm doing this this stream. Yeah, so short answer, I don't know. Theoretical is usually where I would get stuck the most. Yeah, theoretical is hard. I'm glad I found you, bro. I just started the Strang book. Doing it with you will probably be way easier in terms of understanding the subject. That makes me really happy to hear. Don't cheat on your homework, though. Don't copy my answers because they're wrong. They're probably wrong a lot, and they are not very rigorous. But I hope it helps. I hope that these are like fun lectures, or like, I don't know, fun hangout study group or something like that. It would be great to get more and more people actively working on Strang, so that we're working the same problems together. Favorite course in university? All right, you're gonna get me on a tangent. Favorite course in university? Oh my god. Favorite math course? Okay, well, let me think for a second. Alright, I'm sorry, I can't just answer that with one. We're going to have to divide and conquer and think about 4 other Other is easy for me. Out of all of my random classes that I took, wine tasting. Wine tasting was fun. That was a fun class. It was really neat to like learn a little bit about wine, be able to talk about it, be able to tell the difference between two different wines, like be like, this one's a Chardonnay, it's buttery. Yeah, that was a fun class. And then we'd go to the bars afterwards and get properly drunk. Philosophy. So the reason I wrote these three were that I did minors in computer science and philosophy, and my major was in mathematics, in like pure math. So out of philosophy, I would say Asian philosophy, Asian phil, compare contrasting, like Buddhism, Hinduism, Taoism, Confucianism. That was an incredible class, very eye-opening to me about like a different perspective on the world and like just like a very different lens to view the world. I loved it. Asian philosophy or ethics. I don't know. I loved every philosophy class I took. Computer science. Computer science was probably theory of the mathematical theory of programming, because I'm a math major, I guess. Like I really liked the theory class. I have my copy of Sipser right here. Yeah. This book was great. Introduction to the Theory of Computation. Discrete finite automata, regular expressions, all sorts of good stuff. Math. This is going to be the hard one. So we're starting from the easier answers to the harder one. It's got to be linear algebra. I mean, it's just got to be linear algebra. Linear is just so wonderful and beautiful. But that linear class was my real like undergrad linear algebra, my first course in linear, which is sort of a lot of the material I'm teaching right now. I took that my first semester, and it converted me from, I was a biomedical engineering major, and I was going to study chemistry, and then I realized I don't like chemistry, but I do really like math. That's what converted me over. Linear algebra or number theory. Yeah, number theory was beautiful. Just absolutely beautiful. I don't know how to pick between the two. It's like, pick between your favorite kids or whatever. They're just both so wonderful. So, yeah. If you absolutely made me choose, if I had to choose only one out of all of these, it would not be wine tasting. You know what? It probably would be ethics before Asian Phil. It definitely wouldn't be theory of programming. And then between the three of these, I think it'd be number theory. Yeah, number theory wins. What exactly is number theory? Go check out... I mean, they're not very much number theory yet. They're really basic discrete math videos so far, but number theory, I was going to say go check out my videos. I've done 3 so far on number theory. But number theory is literally the study of the whole numbers. The whole numbers, like the integers or the counting numbers. Integers include the negative numbers. Counting numbers are only the positives. But it is things like the fact that it's like the study of like prime numbers. Studying primes, like the atoms of all mathematics. There's just so much cool stuff here. It's like a lot about divisibility and modular arithmetic and My avatar right now is this beautiful result in math that is very, very hard to understand why it's true, but you can prove, or you can state it to like a middle schooler, like Fermat's last theorem, that this equation does not have any integer solutions if n is greater than 2, or if n is greater than 2, and ABC is not 0. Like, it's just incredible. Like, that is, there is no Pythagorean theorem for the cubes. A cubed plus B cubed equals C cubed. There's no Pythagorean theorem for the cubes, or the fourth powers, or the fifth, or any power. It's just gorgeous. Like, how? How do you know that? And the math behind it is very complex, and this problem was solved after I was born. So that's, this is new math. This is new math, like understanding this. So you haven't seen this one before? Math spellbook? You haven't seen Fermat's last theorem? Oh my gosh, today's your lucky day. It is an incredible story. And I will get into it in a little more detail in a future video, because we're supposed to be doing linear algebra right now, not number theory. But yeah, good question. Favorite course in university? You have seen it. I was going to say, it's like it is a popular fact, a popular statement. But when I studied math in college, there was no YouTube. So to me, all of this info was totally new, and I didn't see any of it until I took a course on these subjects. And I was just like, what? What do you mean? I've never seen that before. Nowadays, everything would be so different if I were doing a math degree, and there were YouTube channels like this, or like plenty of others. The Math Sorcerer, or Learning as a Hobbyist, I think, is one. Obviously, like Numberphile. Like, it would be great to have Numberphile today. I think when I was in college, there was Vi Hart, was just starting her YouTube channel. She was like in the early days, and like, of course, like Sal Khan as well. But I felt like I was already beyond, like Sal Khan mostly taught like high school math. But Vi Hart has some cool mathy math sort of videos, at least back then. Paulo, I took discrete this semester, and my professor said linear algebra is the most useful, but number theory is the most beautiful. Exactly. That's exactly it. I'm glad that your teacher's on the same page as me. Like, linear to me is very beautiful too. It's the beginning of beautiful math. But number theory is the most beautiful. Like, yeah, that is accurate, I would say. I don't have chat up. Browser. How do I get a browser? Math, YouTube chat. Where are we going to put it? Down here? Chat is disabled. Whatever. Let's put it right there. And put the right URL. I wish YouTube would make this way easier. Dang it. Oh, okay. Yeah, it is showing up. Vi Hart, I remember watching some of, her stuff. Yeah. Cool. All right. No more questions. It's good to have the chat up so that people can see what I'm responding to after the fact. Even though that is abysmally tiny, at least it's on screen. Okay, so Shilov. Show that the n factorial terms of a determinant of order n. exactly half have a plus sign, other half have a minus sign. Okay, so we're talking about the determinant of a matrix. I said that a matrix is a way to write down the system of equations. You can think of it that way at least. And the determinant is this fancy machine that determines whether or not there is a solution. If the determinant is not 0, then there is one solution. If the determinant is 0, if it is 0, then the system is either infinitely many solutions, or 0 solutions. But what's cool is, if you can calculate something and then it's not 0, then the thing is solvable and it's worth trying to figure out what is the solution. Okay, so I'm going to redo this part. So, rephrasing, just for practice here, we're going to show half of determinant terms have minus sign. That's my short, brief version of the same thing. So this is going to stick in my head a little bit easier. So I can maybe remember this fact in the future. Even though it's not the most precise, rigorous statement of what that problem says, it's still a short version that means that I understand it. I can paraphrase that question. That's a useful technique, I think. Okay, so now let's recall that the sign of a term, I don't know how to call the term, x, is going to be, let x be a term of the determinant I2, 2, ... A, I, N, N. So what we're doing is everyone remember that for any term in a matrix, I represents the row and J represents the column. Okay? So we are taking some element of the first row, we are taking some element of the second row, or of the second column. Did I say row both times? I meant column. We're taking some from the next to last, and then we're taking some from the last. And each of these is a different row, okay? You can't take two from the same row. But we're taking one term from every column and choosing a different row for each column, and then we're multiplying all of them together. All right, what the hell are you talking about? For the people who are new, let's give some examples. For a 3x3 matrix, we have this. These are all of the terms. Okay? Now, the determinant, I can show you the shortcut way that I learned the determinant as, because I just learned it calculationally. You write the dang matrix all over again. A1, 2, A2, 2, this was 2, 2, 1. A3, 2, A1, 3, A2, 3, A3, 3. Okay, so you write the matrix again. And what you do is you take these diagonals are positive, and then these 1, 2, here, that's not as readable as I want it to be. Those diagonals are negative. So what do I mean by that? A11, A22, A33 plus A12, A23, A31. I just grabbed these three right here. So, you with me? These are positive terms. A13, A21, A32. Now, the ones with the lines that are going upward, we subtract. I think of this as, well, yeah, it is A31, A22, A13, A23, A11, and A33, A21, A12. Okay, so these are the 6 terms in the determinant of order 3. And the top ones are the terms of positive sign, and the bottom row are the ones of negative sign. Let's see, does everything match up with what I said earlier? I was saying that for each term, like A11, A22, A33, the first coordinate, if we just look at the sequence of the first coordinate and the sequence of the second coordinate, each of them, like, neither of them should repeat a number. The second term, A12, A23, A31. The first coordinates are 1, 2, 3. And the second coordinates are 2, 3, 1. So this is, in other words, a permutation of the numbers 1, 2, and 3. For both of these, for all of these, they are all the different permutations of the numbers 1, 2, and 3. A13, A21, A32. I'm grabbing these and I'm showing that each of these are 1, 2, 3, and 3, 1, 2. Right? Here I'm writing out the first coordinate, and here I'm writing the second coordinate. That is the first coordinate, which is the row, and this second coordinate is the column. Okay. You with me? So, do you believe me that that these are always a permutation of the numbers 1, 2, and 3? In linear algebra, we always have the fact, recall, in linear algebra, A times B equals B times A for A and B in the field that we're working over. That's one of the important axioms of a field. We need to have the fact that you can multiply first times second equals second times first. So all of these that I wrote could be rewritten in the standard form. Therefore, Shilov's standard form of a single term is always a I1 1, a I2 2, a I3 3. The columns in order is a way to think of it. Because the columns, there we have the first column, there we have the second column, and then there we have the third column. But the rows are out of order. So all we care about is this order of the rows. This needs to be a permutation of 1, 2, 3. Now, finally, let's give this, I have no idea of a good notation for it. I'm just going to call it X, whatever. X is this specific term in the determinant, and often we use sigma to mean the parity, which means, or sigma is often the sign of a thing. It's either plus or minus 1. So it's either plus or minus 1, sigma of x, Shilov defines as -1 to the n. What the heck is n? N I1, I2, I3. Okay. Where n I1, I2, I3 is the number of inversions of the sequence I1, I2, I3. I should go ahead at this point and start moving to n dimensional as opposed to 1, 2, 3 all the time. We are now talking about I1 ... IN. Not just three-dimensional matrices. I recently discovered your channel. Heck yeah, man! Thank you. Thanks for the second like. I see that you liked it. Thank you. Appreciate it. What do you like about it? I'm gonna put you on the spot. What do you like and what do you dislike? What could be better? What should I do more of and what should I do less of? I hope you enjoy it, man. Thanks for watching. Thanks for the sub and whatnot. Okay, so therefore, Shilov says, prove half of x's have, you could say either even or odd inversions. Then my solution is going to be, or my proof or something is going to be that every what's the word? Permutation. That's what I'm looking for. every permutation of n numbers to one term in the determinant. That's a claim. I think that will be fair to say in this book. Every permutation of n numbers corresponds to one term in the determinant. So we need to show that half of the permutations have even number of inversions. I really just kind of restated the same thing, didn't I? Half of the... So... I mean, here I converted this problem talking about linear algebra specifically in terms in a determinant, and now I've simplified that same problem and said that, well, it is the same as understanding permutations in general. Like, if this is true about permutations, then it's true for this problem in linear algebra in particular. And so in group theory, we study the symmetric group, which is exactly the group that studies permutations, like this is a map that takes 3 to 2, 2 to 1, and 1 to 3. Let's say 3, 4, 1, 2 or something takes 2 to 1, 1 to 2, 4 to 3, and 3 to 4. So these are functions that where every number maps to another number. And so, like, if you have a bunch of things, we're talking about permuting, like swapping items in a list. So I would open up my abstract algebra book and remember and show that this is I don't know. I don't freaking know. I don't know. I like this kind of lives, but I would love to see more videos focused on solving certain problems from different areas of math, linear algebra, number theory, discrete maths, etc. Oh, that's the goal. That's the goal. So I'm doing, at the moment, 1 week at a time per subject. I did 3 videos on number theory, and now, over the last week-ish, we've been focused on linear algebra. Next week is going to be calculus. And then I'm going back to number theory. But do you think I should do it more frequently? Should I do all 3 in one video? Because this is a brand new channel, brand new idea. I'm open to feedback. If you all want to see calculus, linear algebra, and number theory all mixed together, I'm happy to do that instead. But right now my thought is 1 subject, 3 different levels of difficulty. like Shilov, this red problem is hard. And then I don't know, maybe just blend it all together. Maybe I'll roll a dice each day and be like, okay, today we're going to do this subject. Roll another dice. All right, we're going to do this level. We'll do a problem from this book. Okay, I'm going to find my book. I'm just going to look at the answer. A beautiful thing about this book is that it has the solutions for most problems. So we can just look at the answer. What is... Yeah, sure. Okay, yeah, sure. Well, what does yeah, sure mean? Which one do you prefer? Up to me? Like, if it's up to me, dope. I've got ideas. We'll play around with it. We'll keep changing. We'll keep changing stuff. Do we have... Oh, you son of a bitch. All right. Hint. Consider the determinant, all of whose elements equal 1. What the hell? Okay. All right, so let's come back. Here's what I was working on yesterday, and I had an approach thinking like every time that you add a number in a sequence, it is either in order or it's out of order relative to the other numbers in the sequence. I don't know if that's true exactly. I don't think that that's like a completely fully baked thought, and I don't think it's true. But I don't think it's like completely wrong. It's just like I kind of know roughly the abstract algebra way to answer this. So it's hard for me to care to solve it this way, but consider the determinant, all of whose elements equal 1. I don't know what he means by that. Is it the determinant of the matrix where terms all equal 1? Is he saying that like A12, A21 equals 1? Like the multiplication of the elements equals 1? Or the matrix where every element is 1 and then to take the determinant? Because these are different, right? Like this option could include things like 2 something 1/2, I don't know, 4 1/4. I think the determinant of that, you take the downward diagonal 2 times 1/2, and then you subtract 4 minus 1/4, or 4 times 1/4. I don't know if that's what he's referring to or what, but I don't see why that hint helps us, so we're just going to come back to this. Still going to keep this one in the hard column. I don't get it. I might just look up the answer next time. I gotta pee super quick, so I'm going to be right back. You can do one stream for one subject, or if the stream is going to be longer, you can change it up once in a while. Yeah, maybe. That's a good... I don't know. Yeah, I'll just keep playing with it. Today we're doing a bonanza. We're doing a bonanza, meaning that it's going to be a long, like 3-hour stream or something. I got nothing else to do today. So that's fun. I hope y'all hang out and chill and What problems are you all working on? Are you all doing math? Give me some of your homework problems and I'll solve them for you. Why not? Why not? Or or really just, share. Let's share what we're working on. Research level math, very welcome as well. High school math, anything. Let's all just nerd out about math. What are we all working on? Like literally just write down the problem that you're doing on your own. In the comment section too, if you're watching this after the fact, which I don't think anybody does. Not too many people do, but some people do. I'm gonna be back. Be right back. All right, hello. Let's switch over to the horizontal iPad so I get a little bit more space on the screen. Where is it? I don't know. I have to double click things nowadays. OBS used to be different on that. And this one, we do have people chatting, so let's put chat up. Eating right now. Once I'm done, I'll try chapter 1, section 1 of How to Prove It. Nice. That is a terrific book. Everybody loves it. I haven't tried it yet. How to Prove It. Where is it? I feel like there's another book by Paulia about proofs. Because I used to think that it was Paulia's book that everybody loves and recommends. What is Paulia? Paulia proof problem solving book. I swear there's a book by Paulia. How to Solve It. That's the one that, that's the other option that I've seen. Yeah. Yeah. Yeah, I've heard good things about How to Solve It, which is, it fits with the usage that a solution is more general problem-solving techniques, and a proof is a specific mathematical, rigorous argument. Yeah, I've heard good things about both books. So if you're going to look at Chapter 1, Section 1, what is that? Truth tables? Lovely. Yeah, I mean, that's where my class started too. Yeah. Yeah, truth tables. De Morgan's Law, truth tables, all that good stuff. Yeah, vaguely remember all that. It's a good way to like just really carefully learn proofwriting techniques. Sorry for the noise. Sorry for the feet noise. Whatever. Okay. Well, Shilov on determinants. Shilov is bothering me. Let's try. I don't know what his hint is talking about, but the claim is that the claim is that every set of permutations of n elements has half of them have even inversions and half of them have odd inversions. I don't know, it's just like some kind of symmetric proof, like it needs to be the case. This feels like a proof by induction, inductive step. So it's clear for the base case, those are the two permutation sequences. Inductive step, assume it's true for Sn, prove that it's true for the next, for n elements. If it is true for I1 through In, then when you add let's write 1 dot dot n plus 1. When you add that extra term into a, how do you say it, like a list or a sequence? When you add the extra term into a sequence, oh, wait. I don't know, like you can, there are n plus 1 places that you can put that one element, and then n plus 1, if there are n plus 1 places that you can put it, if you put it all the way on the right, then there are 0 additional inversions. But if you move it 1 to the left, then you have 1, and then we get dot 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 n, which is then the triangle number n times n plus 1 divided by 2, which is either even or odd. Where are we going to use the inductive hypothesis? So like that, if there are I don't know, we're getting so much closer. We're getting closer and closer. Maybe append n plus 1 to the end of each permutation in Sn to form a new stat. Hey, that's basically what I just started getting to, right, Paulo? Like, I just saw that, essentially, right? Like, we assume Sn and then prove Sn plus 1. And I was thinking in my head, yes, that these are, it's obviously not just always 1 through n, but like all of the different elements of Sn. And then you append n plus 1 after it. And then it's the number of permutations or the number of inversions of the original, and then the last one is it's greater than every other element. So it's still the same number of inversions, but then there's all the different places that you can put it. Like, it feels so close. Like, I feel like we're almost there in terms of getting that, like, inductive step. It's something along these lines. I don't know if this is like the kind of argument that he would assume. I wonder if there's like a nice theory. Is there anything that he wants us to be able to assume and reference in terms of no, do not, no.
Here's what
What's going on? All right. Because, like, he doesn't use Sn. He doesn't really describe the symmetric group or, like, describe permutations very carefully. This is, like, page 3. Okay, I've looked and actually read the section again for the first time in a long time, and he's very careful about saying by the determinant D. Let's write some of this stuff out. Definition of the determinant per Shilov. By the determinant D of the matrix, is meant. That's a weird translation. I know that the original was in Russian, but it's meant the algebraic sum of the n factorial products of the form 5, and he just says, by the determinant D of the matrix 4 is meant the algebraic sum of the n factorial products of the form 5, and 5 is this thing. He uses this awful notation of A alpha I 1. I hate that notation, so I'm immediately changing that to I's just so much easier to read, in my opinion. I want to be snarky for a second just to feel better about myself because I don't know how to do this problem. Each preceded by the sign determined. Also, Paulo, nice to meet you. You know what I mean when I'm talking about SN, so it sounds to me like you might study mathematics. Are you what kind of math do you study? Are you in university? Maybe you answered this earlier. I forget. Oh yeah, you said I took discrete this semester, and your professor said stuff. But you know about SN. That's cool. If you just took discrete, that's pretty great. Each preceded. Are you a math major or computer science? Perhaps. Usually CS does discrete. I guess it makes sense that you might have seen the symmetric group in discrete. Each preceded by the sign determined by the rule just given. It says D equals the sum of -1 n I1 in a I1 1 ... a I n n. And then here's the part that I wanted to take note of. Hereforth the products of the form 5 Yeah, so exactly as I thought, the terms are the products of the form 5, which is what I expected. They're the terms of the determinant D. The elements Aij of the matrix 4. Wait, the elements Aij of the matrix 4 will be called the elements of D. This is the part that I thought was new to me. Like, wait a minute, what are the elements of a determinant? Elements is different than the terms of the determinant. The elements are the individual like scalar numbers that are being multiplied together in the terms. We call the elements of D, and the order of 4 will be called the order of D. So the order of the matrix is the order of the determinant. And blah, blah, blah. We will use these notations interchangeably. D equals single bar and then we also use det Aij. Okay, well, that's fun. I feel like we made a tiny bit of progress. K plus 1 over 2, K plus 1 factorial over 2 equals K factorial. Interesting. Yeah. think that you're onto something there. Hint from Paolo, friend of the channel. Thank you. Yeah, I think that we're going to be using these kind of like binomial coefficient facts or something. K factorial over 2 times, what? I can't read this very well. Plus K factorial to, okay, well, I'm going to have to read that a little bit more, but a little bit more carefully. I agree with you that thinking about the next like I'm thinking of Pascal's triangle and like the binomial coefficient, binomial coefficient identities. And choose K. And n plus 1, choose K equals ... and I'll look that up. I think it's something along these lines. But I'm feeling a little stressed out about this problem, so let's move on. I want to do something from Strang. The goal right now is to learn some computational linear algebra, as fun as the theoretical stuff has been. Strang, let's work. So I've been doing several from the first section. I want to continue with section 2 or 3. Lengths and angles from dot products, that's kind of boring. Let's get to matrices. String 131. What is 131? That's cool that you're taking math courses. Oh, and you're planning on actually switching from finance to math. That's dope. You will be a highly sought after quant if you do it. It's a very good field to go into. Like, if you really want to stand out, I think in finance, you study math. And then you go do boring applied math, like finance. Good for you. My copy of Strang is arriving later today, and I'm excited. I wish that it would have shown up before the Bohnanza, but it didn't. Strang 131. All right. Describe the column space of these matrices. Point, line, plane, and then it says, or all of 3D. I'm going to go ahead and write 3D as R3. A1 is 215, 216. A2 is 100, 110, 111. A3 is 1, 2, 1, 5, 10, 5. And A4 is 0, 0, 0, 0, 0, 0. Okay, so this is cool. This is stuff that I know. let's recall or learn for the first time and state it for the first time on the stream that the column space of a matrix equals the span of the column vectors of the matrix, which is a set of all linear combinations A v1 plus dot 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 a1 v1 plus dot 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 a n v n by m. We would usually use m here. I don't know. Something like that. We're taking all the possible combinations of vectors, and so the column space, which there's probably a notation for, of the column space of A1 is the linear combinations of the vector 2, 1, 5 and 2, 1, 6. I think that some books will use this to mean the space generated by these two vectors. If not, that's a nice notation and I like it. Like angle brackets means every combination of these two things. So one of them is just like ever so pointing in a like ever so slightly a different direction than the other. I can see that this is going to be this is going to create a plane which is a subset of 3D space. The column space of A2 is the space spanned by 1, 1, maybe span. Maybe you write the word span 0, 1, 1, and 0, 0, 1. There's no combination of these two that can get you the first vector. It's linearly independent from vectors 2 and 3 because the first element is non-zero. And similarly, the second vector is linearly independent from the third because the second coordinate is yeah. I don't know. Those two are clearly linearly independent. We have three independent vectors in 3D space, so then since they're all linearly independent, then the column space is going to be all of 3D space. Lots of hand-weavy arguments here. That's okay. That's okay. We're a hobbyist. In fact, I feel very good that now it is a span of 1, 2, 1 and 5, 10, 5. 1, 2, 1 and 5, 10, 5. So just reiterating, I'm writing down the columns as vectors. Hey, have to go, but Thanks, dude. Thank you for stopping by. It means a lot. I'm glad that you're enjoying it, and see you next time or sometime in the comment section or whatever. Thanks for stopping by. All right. Well, V2 is 5 times V1, so they're the same damn. They're the same damn line, and then therefore that is a line. We've got a line. Zero, 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 zero. Well, that's clearly a point. Wait. Yeah, because any multiple of 0, 0, 0 is still 0, 0, 0. Whereas in this other one, you have many multiples of 1, 2, 1. Yep. Cool. We did one. There's 1, 3, 1 in the bag. Feeling good. I circled it as a to-do. We did it. Let's just do Strang 1, 3, 2. Why not? Why not? Gotta rebuild our confidence after that Shilov problem, you know? Strang 1, 3, 2. Find a combination of the columns that produces the zero vector. Column space equals plane. What does that mean? Column space equals plane. The trivial combination 0 times every column is not allowed. Okay. Oh, okay. It's just weird writing, if you ask me. It's like, yeah, okay. Find a non-trivial combination of columns that produces 0, 0, 0 is what another book would say. But this is very spelled out, and it's nice. The trivial comb 0 times every column is not allowed. It's funny to say it's not allowed. Like it's like rules in like school or something. Like I don't know why that's so funny to me. That's very different. And then it says a big ol' hint. Which columns are dependent on earlier columns? It's just funny. Yeah, I don't know. All right. Let's not be annoying. 1, 2, 3. Hey, it's my favorite matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. I already did this one the other day. I did this one when we were like starting out, and I used this as an example. That's so cool. I came up with the exact same example as Strang. I remember it off the top of my head. C3 is 2 times C2 minus C1. Was that correct? Yeah, 2 times C2 minus C1 is 2 times C2 minus C1. Yeah, I remember that off the top of my head. That's cool. So there's A1. Here's A2. Where are we? 147. Oh, and we did the exact same thing here. I came up with this string problem. I came up with this exact same problem. That's so cool, because I thought, hey, what happens if you write it this way instead? I invented this problem, y'all, in like video 1. I'm so proud of myself. Probably video 2, linear algebra video 2. And the magic trick, the magic thing that we find is, at least in this example, and I don't remember my theory well enough, but this is so cool. We get the exact same linear combination in both of these. So if you don't see what I'm talking about, 2 times C2 is 2 times 4, 5, 6 minus, I was talking about the row space, but row space is equivalent to column space, and we'll see that. We'll see that as we go. 2 times 4, 5, 6 minus the first column, 1, 2, 3, is 8, 10, 12 minus 1, 2, 3. Oops. Did I screw this up? Oh, yeah, no, that's right. Yeah, we're doing fine. 8 minus 1 is 7. 10 minus 2 is 8. 12 minus 3 is 9. That 7, 8, 9 is right there. This column. And then you can see the same thing in A1. Cool. Pre-solved. I've already done that one. That's great. I feel very proud of myself, y'all. I don't know if anybody recognizes how cool that is. I came up with one of these problems on my own. Next. Was there another question? Oh, wait. Yeah, then the next part of that question was find a combination that produces 0, 0, 0. So if we have C3 equals 2C2 minus 1, C1, then we know C1 minus 2C2 plus C3 equals 0. I mean, we found that they're equal, so then if you subtract one from the other or whatever, then that's going to be the 0 vector. Next we got Strang 1, 3, 3. What do we have going on here? What's going on, folks? I should make some food. I should do some food or something. Thanks for the likes, everybody. Hit the like button. It means a lot to me if people give this a like, you know. Brand new stream. I want to speed run 0 to 1,000 as quickly as I can, just for my ego's sake. It took me a while, y'all. I just hit 1,000 after 6 years in my guitar stream. It took 6 years to hit 1,000. I got it last month. I want to see if we can get to 1,000 in 2 months in this stream. I feel that's ambitious. I feel that's very ambitious, but we might be able to do it. I think mathematics is actually a much more universal thing than classical guitar, especially classical guitar practice, which is what my other channel does. I think people watching somebody get stuck and having a hard time in math, having difficulty in math, that's a super universal thing. Everybody has been frustrated at math. We'll be having fun and solving problems easily sometimes, and then we will be getting totally stuck at other times. Describe the column spaces in R3 of B and C. Oh, this is cool. Okay, so writing matrices in matrices. That's cool. I like that. I like that Strang did this. 1, 2. What's the pattern here? 1, 2, 3, 2, 1, 3. Interesting. 1, 2, 3, 2, 1, 3. Interesting. Okay, so writing this one out explicitly, we have 1, 2, 2, 1, 3, 3, and then negative b. So it looks like we're going to have negative 1, negative 2, negative 2, negative 3, negative 1, negative 3. Okay. Well, I don't think that there's going to be anything particularly... There's no new geometric space that's spanned by these new columns because, well, how do I want to say this? Let's say that C1, let C1 to Cn be the column vectors of A. Then I can say C3 is negative C1, C4 equals negative C2. So I can like very clearly write down exactly how they relate. So we just need to see that C1 is linearly independent from C2, not a scalar multiple. Then, therefore, the column space of this matrix C is, well, it's also going to be equal to the column space of B. Column space of B is two vectors in 3D space generate a plane. Yeah. I think that's good enough. I think that's accurate. It's fun studying and joining you in this mathematical journey. Hearing you on stream makes me feel like we are all doing research in different fields of math within the same room. That's such a cool vibe. I love that. I think that that's very cool. I hope that it can continue feeling like that as we keep going on. Yeah, I think that's really great. I'm gonna like screenshot that or something and share it with my old teachers. Or I'm gonna pin it. Why don't we do that? Why don't we pin that message? That's so cool. Thank you. I'm gonna make some food. Why don't I write down the next problem? Y'all can think about it on your own and try to solve it. If anybody out there is following along that carefully. Where are we? 1, 3, 4 now, I think. We've already solved 3 and I want to cross it off. Oh, we've already done 4. So we're now on 1, 3, 5. We're just ripping through this section. 1, 3, 5. is no problem. Honored to be pinned. Heck yeah. It's not going to be that rare. Like every time there's a comment that I like, I'm going to pin it. Multiply the same. Oh my god. Okay, multiply the same a times x and b. I don't like his notation here. And b times y and I times z using combinations of the columns of A and B. Alright, A and B and I. Why are you doing the double and? That bothers me. Of A, B, and I. As in, A equals 1 times column 1 plus 2 times column 2 plus 3 times column 3. What the hell is he talking about? Okay, so the matrices that he's referring to is in the prior problem. AX is... Oh, I see it. Okay. 2, 4, 0, 1, 2, 1, 2, 4, 0 times the vector 1, 2, 5. BY is 1, 0, 0, 1, 1, 0, 1, 1, 1. Lower triangular matrices have a lot of great properties. There's theory around those that we will study later. IZ equals 1, 0, 0. This is the identity matrix, 0, 0, 1 times Z1, Z2, Z3. So for any numbers, what do we get? Interesting. Okay, I think I get it. Alright, I'm going to be right back, y'all. Be right back. Here's this problem that you can chew on if you want to. I'm just going to make some food really quick and be back. Cool. All right, y'all. I made a meal. I made a fully delicious, nutritious, nutritionally complete meal. Very cheap. Huel, sponsor me. Sponsor me, Huel. Send me free food so that I can teach people mathematics on the internet for free. That would be great. I'm trying to save some money. This stuff is delicious and affordable. Cheers. Love it. I genuinely do love Huel, honestly. I wouldn't recommend it. Hippies, sponsor me too. Hippies are really good too. Welcome back. Good to see you. Good to see you again, Math Spellbook. Well, that's really annoying. I don't like how the pinned message looks awful on stream. Y'all, YouTube needs to step up their game on the embedding chat in stream experience. It's really awful compared to Twitch. Like embedding chat in Twitch, way more beautiful, way nicer. YouTube? Nuh-uh. Nuh-uh. All right. That's why I prefer Twitch for streaming. Yeah, I don't know. I have strong opinions on the two. I think that YouTube has such better reach. Like, YouTube's available worldwide. I don't think that... Well, YouTube's available in more countries. I don't know if Twitch is available in India, for example. Like, there's a lot of people out there. YouTube's more, like, mainstream, let's say. So, I got used to YouTube for classical guitar. Classical music is a pretty mainstream subject. Like, I want to be able to target, like, an older audience. Twitch just has, like, a certain culture and a certain demographic. I think it skews a little bit more male. It skews a little bit more towards video games and memes and stuff. We're serious business people over here. We're serious adults. Everybody's on YouTube. Not everybody's on Twitch. So I like the idea of trying to build this stuff on YouTube. But on the technical front and a lot of things, YouTube could be so much better. I would just stream on YouTube and upload VODs or stream on Twitch and upload VODs on YouTube. Yeah, it's just too much work, honestly. I'm thinking about doing Twitch again for this because I think that this is super cool. And rating, especially, is one of the biggest product flaws in YouTube. There's live redirect, but I've never seen a single person use it. I've tried to use it. It's impossible to use as a streamer, and it's such a bad name. It's so stupid. I don't remember if I've mentioned it, but I used to work at YouTube, and I don't know. I tried to tell people. I tried to give my feedback, like, hey, I'm a streamer, and I have XYZ opinions, and people just don't care. That was my experience. People just don't care. Too hard to get anything done at a huge company. So, that's not what we're doing right now. We're not complaining about YouTube. We're solving this problem. Okay, so this is going to be cool. I bet we're going to find some magical properties here. So it's saying we're going to take that number and multiply it by that column. I remember some of the stuff like so vaguely, but I think that this is a theorem that we like prove later on or something. So this is for matrix A. For matrix B, we're going to have 4 times 1, 1, 1 plus 4 times vector 0, 1, 1 plus 10 times 0, 0, 1. I don't know if there's anything special here. I think so. Z1 times... I think maybe we end up getting the same exact... the same matrix or something? Yeah. Yeah, we might get the same vector. Yeah. Yeah, I'm pretty sure that's what happens. 0, 1, 0. The same vector as when we multiply them by elements one at a time. Okay, so here we've got 2, 4, 0, 2, 4, 2, 2, 4, 2, and then 10, 20, 0. $14, 28, 2. Second one is going to be, I'm going to jump right ahead. 4, 4, 10 is 18. Here, Z1, Z2, Z3. And if we compare this, what the heck? If we compare this stuff to what we had yesterday when we solved one of these problems, or the day before, Yep, we got the same. Yeah, when we multiplied them as dot products of the rows and columns, we got the same numbers. 14, 28, 2, 4, 8, 18, Z1, Z2, Z3. Just to be sure about that, 14, 28, 2, 4, 8, 18, and Z1, Z2, Z3. 14, 28, 2, 4, 8, 18. Neat. Isn't that so cool? That's not obvious at all to me, like why that would be the case. I think we need to prove that. And that will be a theorem that we prove at some point. Maybe in this section, I don't remember. It happens, at least you are streaming what you like to do. Yeah, I don't remember what it happens refers to. The YouTube product flaws that I'm complaining about. Yeah, it's whatever. Yeah, that's really cool. I forgot that that's a fact. 135. I forgot that that's a fact. Honestly. That you can multiply those elements by the column vectors and then get the same answer. Yeah. Neat. How much farther are we going to go? YouTube product flaws thing and people not listening to new ideas. Yeah, it's fine. It's whatever. It's just really hard to... It's really hard to... Yeah, I don't know. I mean, they already hear a million complaints from users all the time. Like, I'm sure that they already have tons of data. And it's just that you have 1,000 things that you could do at any given time. Like, it's hard to prioritize And there are very smart people deciding what to do first and what order to do things in. I still think that it helps to be able to talk to somebody who uses like the streaming side of the product more frequently. Like not have to do like a full survey or something. I would love to go back to YouTube and work on product. Like I'd love to help build and design what features to work on. Like what bug fixes, like prioritize, like do this first, do this before that. Like a lot of the new AI stuff, not great. Don't love it. Just gets in the way. Just annoys me every single time I see it in YouTube Studio. I think, why isn't this old bug fixed? I hit this bug every single day and it's so annoying to me. And now there's this new AI stuff that's just getting in the way and making it worse. Yeah, I don't know. I could write down like a lot of product criticisms, and some of them I think are more obvious, and some of them are really non-trivial. And like, I've got some clever ideas over here, y'all. I've got ways that I would suggest YouTube could be better. In problem 5, the last one we just did, how many independent columns does A have? How many independent columns of B? How many in A plus B? Interesting. Let's rewrite this. There it is. Oh wait, we also want B as well, so let's just grab both at the same time. Let's remind ourselves of what we're looking at. Independent columns, well, clearly, yeah, there's only one independent column. Oh, nope, there's 2. Column 1 and column 3 are the same, so clearly they're not independent. The number of independent columns of A is 2. Number of independent columns of B is 3. What is A plus B? I bet that this is now going to have 3 independent columns. I'm just double checking something from a moment ago. Yep. Let's see. So, 2 plus 1 is 3. 1 plus 0 is 1. 2, 2, 4. Oh, wait. Nope. Boop, boop. I'm a dummy. This one's a 4. 5, 3. And then, 1, 2, 1, 2, 1. Did I do that right? 3, 5, 1, 1, 3, 2, 2, 4, 1. Yes. The number of independent columns of A plus B is... How can I prove this? I'm going to use C's to mean column 1, column 2, column 3. And if 2, 4, 1 equals, that is, if C3 is some multiple of C1 plus some multiple of C2, can we solve this? We'd have 3a plus b equals 2, 5a plus 3b equals 4, and a plus 2b equals 1, right? I'm going to do it in the Gaussian elimination way. Subtract 3 copies of that from that. Well, no, let's be more. Let's do this more slowly. 3, 1, 2. I'm just rearranging the rows. One, two, one. Subtract 3 subtract row 1 from row 2 and row 1 from row 3 to eliminate the first number. So we need to subtract 3 copies of row 1 from row 2. So 1 minus 6 is negative 5. 2 minus 3 is negative 1. And then subtract 5 copies of row 1. So 3 minus 10 is negative 7. So something's looking bad. And then 4 minus 5 is negative 1. So we would get the impossible case of we would get this impossible case where b is 1/5 and b is 1/7, if I did this correctly. So that proves that what are we proving? That proves that you can't write. That proves you can't write the last column as a combination of the first two columns. So C3 does not equal A C1 plus B C2 for any A, B. So therefore, the number of independent columns of the two matrices added together is 3. I think, I don't know. I feel good about that, but I'm not, I feel like just like a little bit like slightly shaky. I feel that there could have been a cleaner proof or solution of that, but that, I think that that's right. 136, we did it. Feeling good, feeling good. Don't really feel like coming back to it ever. All right, well we did a good amount of Strang. We solved some good problems. I want to look at Axler. I want to look at definition of a vector space, section B from Axler. At least you have experience working in tech. I have an English degree and super into STEM fields, but better to create opportunities than chase them. Yeah, yeah. Well, an English degree, I imagine that you're good at writing, and mathematics, a lot of mathematics turns into writing and reading, like reading arguments and analyzing an argument. I don't know, like, the ability to write well is very important in math. So it's not like it's a completely separate skill set. Like some of your English degree skills will transfer over, I think. But yeah, it is different. Just straight up, it is definitely different. And sometimes you do want to just create opportunities. Like I would love to teach somebody linear algebra. I would love to get a student that I can tutor in linear algebra or abstract algebra. But if I put up flyers or something like in my town, there's not going to be a lot of people looking for a linear algebra tutor. So like sometimes you just need to create that opportunity for yourself. Like create a math stream and like build a community, like create the thing that you wish existed in the world. Create the concept of a practice stream or whatever. Yeah, that's my thought. That's my take on it. All right, so we're going to do Axler section 2 now. Because Strang is starting to bore me. Axler 1b. This is something about the definition of a vector space. I get what you mean. Yeah. Where are we? Open recent. Do I have... Axler's book is terrific because it is available for free on the internet. He just gives away this book for free, and it's incredible. And something that's cool is that it's a medium difficulty. It's a second course of linear algebra. A little bit more theoretical, a bit more proof-based, like what we're doing in Shilov. But his whole thing is that he doesn't teach determinants until way later. In Shilov, the determinant is like problem 1. It's section 1, problem 1. Axler has a strong opinion that linear algebra done right means study the abstract theory of vector spaces before you learn about the determinant. It's pretty cool. I think that's roughly what my course did also, honestly. I really do think so. But we did learn the determinant. We definitely use the determinant. Dang. Does he really put off the determinant until section 9C? There's only 9 chapters, and then there's sections within those. Or is that only... Yeah, multilinear algebra and determinants. So chapter 9... Wow. So we're going to get all of this stuff without the determinant. We're going to get eigenvalues. We're going to get... Ooh. Too bad you all can't see this, but that's fine. Polynomials. Okay, he's got a whole section on polynomials, I think, as an example of a vector space. And factorization of polynomials. Oh, this is going to be a cool book. This is going to be a cool book. Products and quotients of vector spaces. Matrices representing a linear map by a matrix. Vector space of linear maps. Yeah, this is going to be fun. It is not an applied linear algebra book, though. So that's the... My goal was to learn some applied linear algebra, but now here I am just like geeking out about theoretical linear algebra again. That's fine. Answer 1B1. Prove that negative v equals v for every v in a vector space v. Excuse me. All right, he used the word prove, so I will too. It is true. This is a proof. Okay. So, by definition, negative v is some vector w such that v plus w equals 0. Then negative v, negative v equals w such that negative v plus w equals 0. Negative v plus negative v. I don't know, this is kind of weird to... Negative v plus negative v equals negative v plus v equals 0. I mean, really, here I'm using the axiom can I use that? No, I think that this is pretty squishy. This is like kind of assuming that the negative here, that these are both elements A and F and B and F, and that I can just multiply those two and say that it's AB, and that negative 1 times negative 1 equals positive 1. But this isn't really part of like the idea of a negative 1 in a field F. Does that always exist? I mean, 1 always exists in a field. Therefore, -1 exists because because every element has an additive inverse. Because 1 plus -1 equals 0. We need, there exists an additive inverse. But then from that, do we know that -1 times -1 in a field equals +1 in that field? So these are abstract concepts of 1, not the regular old 1 from the real numbers and 1 in the complex numbers. But it behaves extremely similarly. It's just that I can't say -1 times -1 is +1 the way that we can in regular math, I think. So I'm cheating here if I just say that those two, like if you multiply a negative by a negative, you get a positive. I mean, I think it's generally true in any field, but I don't know that for a fact. So I think that this part is not on firm ground yet. It might be true, but oh. Well, I'm confusing myself. Okay, so by definition, -v equals w such that v plus w equals 0, the additive inverse. We see w equals v. It's really something like this. Like we see that w equals v satisfies this equation. Minus v, which we know exists, and then plus v equals 0 by def of minus v. So v is the additive inverse of minus v. Yeah, that's like, it's kind of like a little weird, like a little circular. It's like where it's such ground truth, like we're so close to the axioms that a lot of these arguments feel like you almost just repeated the same thing. But that is formally, I think, a decent argument that that the additive inverse of minus v is v. Yeah. I mean, minus v exists for any vector v. So minus v plus v equals 0. Then v equals the additive inverse of minus v. I mean, that's kind of another similar way to say the same thing. Or it is the same. Like, yeah, that works. That's good. 1b1, done. One B2. I don't know if any of this makes sense to y'all or not. I think so. I don't think that this is too crazy right now. Especially if I'm talking to somebody who has been working through how to prove it. I think that makes sense. Axler 1b2. Suppose A is in F, V is in V, and AV equals 0. Prove A is 0 or V is 0. Let me check chat. I got the book Linear Algebra Done Right. I really need to practice linear transformations and after. Yeah, this is the book Linear Algebra Done Right. This is exactly it. It's really nice. Really, really nice. And it is free. So anybody can download this book. At some point I will set this up just for convenience. Ladder.themathhobbyist themathhobbyist.com. I will set up this URL to point to linear algebra done right by Axler. Whenever I say Axler, I mean linear algebra done right. Which I don't know if that's the best way to teach linear algebra. I wouldn't say it shouldn't be your first introduction to linear algebra. Your first introduction to linear should be something more like Strang. That's why I'm mixing the two together. Like, I'm trying to show first and second and potentially third courses on linear. So we're proving AV equals 0 implies A 0 or V 0. We might prove this by the contrapositive. If you want to prove a statement A implies B, you can also prove that not B implies not A. So what we can do is assume not equals 0 and V not equal to 0. We want to show AV is not equal to 0. If A is not 0 and V is not 0, then the vector space is not the single point 0 with any field F. There's more than one element in the vector space if V is not 0, right? If A is not 0 and V is not 0, then the vector space is not the 0 space. then AV is oh no, we can say AV exists and so the additive inverse of AV exists. Whatever the heck that is. And then the two should add to 0. And then we can say that from problem 1, we know that the additive inverse of minus AV is AV. So we can yeah. So then, because of that, the additive inverse of minus AV is AV, as you would hope would be true. So wait. No, I don't know if this is the right direction to go. If A is not 0 and V is not 0, we want to show AV is not equal to 0. I don't think that this is very rigorous right now, but I think that this is the general strategy I'm going to want to use. Like A is not 0 and V is not 0 implies AV is not 0. We could try to prove it by contradiction instead of contrapositive. Those are like two different proof strategies that you would learn in that Velleman book. Just seems very... I need to remind myself of the axioms. I feel like once I see it, I will get it, or like some of the results that yeah, some of the theorems that he does have in the section. We do have some theorems, including 1.30, 0v equals 0 for all v, 131, a0 equals 0 for all a, and 132, negative 1 v equals negative v for all v and v. I feel like maybe 132's proof might be illuminating because it's going to be kind of similar in basic idea and structure as this problem that we're doing. So let's see how he proves 132 and just kind of copy it out verbatim and try to understand it as we go. For every vector, we have okay, let's pause here before we continue too much further. I'm starting to just mindlessly write this down. Okay, so we do have the number -1. We have, which is something that I was wondering about earlier. I was like, we have to prove that it exists, but the number -1 certainly does exist. Where is it? Ooh, the set of functions from S to F. Ooh. Where does he first start using the number -1? Because it is not obvious that the number -1 exists, and it's not true that it's always different than +1. For sure, 127 is a very useful theorem. The other things in between are definitions and notation and whatnot. Unique. I'm thinking of this one in my head without stating it, because I know it is true that every element has to have a unique additive inverse. You can't have two different numbers that both annihilate the vector. Yeah, okay. All right, so he just introduces -1 without showing that it must exist, unless it's in the prior section. Unless it's in the prior section, does he define a field? Yeah, he doesn't start using the number -1 until this theorem, I think. Yeah. Yo, how's it going? Atlin, how are you? What's up? We're trying to study some mathematics over here. I studied math in college a long time ago, and now I am trying to bring it back. Bring it back into my tool set. Because it's fun. Just because it's freaking fun, y'all. Just because it's fun as hell. Not because I want to make $1 million, just because it's fun. Alright, so, yeah, he does use the number -1 times a vector, but he doesn't explicitly show that -1 exists. I mean, we know that for any field, we know that 1 exists. And we know that for all elements in a field, -a exists. So then in particular, -1 is in a field. Yeah, the additive inverse of 1. So I'm just overthinking it. Like, yeah, of course, the additive inverse of 1 exists because 1 exists in every field. For every vector, we have the v plus -1 times v. Oh, okay, yeah, great. So we know that 1v equals v for all vectors. That's I don't think that's a theorem. Maybe that's a theorem. I mean, it's pretty clear. Oh no, yeah, it's a definition. It is part of the definition of a vector space that there is a multiplicative identity. Yeah. That there's a multiplicative identity, 1v equals v. Yeah. Okay. I'll keep that there. Why not? All right, so we know this identity, this number 1 exists, and we probably prove that that number exists and is the same one as the one in the field. And then here we use this great distributive property, which is a axiom. It is like an assumption that we have to state that when you have two numbers, two scalars, you can pull them out to like one scalar times one copy of the vector. And by definition, -1 is the additive inverse of 1. So this number is 0, and now we have 0v. And then 0v is always 0. So now we know that, what is it that we're proving? -1v equals negative is the additive inverse of v. So when we add this minus 1 times v, that it does equal 0, which is the definition of the additive inverse of the vector v. Yeah. All right, so that's a reminder of what these types of proofs look like. And so here, then, maybe from here, now I know I think since we know that the additive inverse of v, I think we know minus av is equal to minus a times v. I think we know that. So then we can use like the distributive property a plus minus a times v, and then a plus minus a is 0 by definition of minus a. And now we have 0v, and I think it's a theorem, or we definitely know that 0v always equals 0. So what the heck? I'm so confused. Let's just come back to this one. I feel like I need to work on this one without talking out loud. Hopefully physics enthusiasts are welcome too. Absolutely, of course. Of course. Anybody who's mathy, I mean, y'all are super mathy, and linear algebra is so necessary in physics. I know that it's kind of critical. Linear algebra is critical in quantum mechanics and kind of advanced classical mechanics. Linear is super useful in physics. So, of course. Yeah, I just want to come back to this one. I don't know why this is tripping me up right now. I'm so rusty. I am so rusty. Let's get a fresh sheet. What we're trying to show, let's remind ourselves, what are we doing? What are we doing here? We're showing that AV equals 0 implies that A equals 0 or V equals 0. And I want to do this by contrapositive. A implies B. To prove that, you can also show the opposite of B implies the opposite of A. I still think that that's the way to go. So assume A is not 0 and V is not 0. Then we want to show that AV is not 0 as well. If A is not 0, I think we can definitely say that, which is the same as AV plus 0V. I don't think we're getting anywhere interesting here. Yeah, we're all rusty. Yeah, it's okay. We're all hobbyists here. We're all rusty. That's fine. This is a encouraging, positive community that we're trying to build. How can we show what would be the way to show that AV is not zero? How could we show that it isn't zero? We could show that the additive inverse of AV maybe is not zero. Perhaps. We know that there has to be some additive inverse. Oh, wait. Oh, since there is an additive inverse, this equation must be true. There has, for whatever AV is, there has to exist another number that you can add to it to equal zero. The additive inverse exists. I'll just say that. Additive inverse exists. Then, by the distributive property, we have A minus A times V yeah. I don't think that really gets us anywhere. We know that that's true. I think we just proved 0V equals 0, not the thing that we're looking for. We want to show AV is not 0. Let's try by contradiction. No, let's try it more directly. AV equals 0. We're not using the contrapositive. We want to show that implies A equals 0 or V equals 0. We know that that either one of these cases would satisfy the equation because of axiom, the existence of the zero vector. The zero vector has to be, that has to exist such that any multiple of it still equals 0. And then the other axiom that the existence of 0 such that 0v equals 0 for everything. I think that's a theorem, not a... These aren't quite axioms, but they're like simple theorems that come out of the axioms. For sure, we just showed that one. And the 0... I think that this other one has been shown by now. Yes. Yeah, I've got both of these. They're written as 131, theorem 131, and this one is 130. So either A equals 0 or V equals 0 both satisfy the equation, but that doesn't show that those are the only options. Like, is there another case? If A is not equal to 0, then minus A is also not 0. And then we have like AV equals yeah, if AV equals 0, the 0 vector, and 0... No, that's not... What the heck am I doing here? It's been a while. Thanks to the stream, I've gotten at least 4 problems done. Heck yeah. I'm happy to hear that, man. That's the goal here. Like, let's all just be study buddies and work on our problems together. I'm so rusty on this stuff. I just want to come back to it later. We're so close, though. I feel like we're on the right track. 1B2. I am rusty as heck. Making partial progress. Like, some of the, like, ground truth axiom proving, or, like, ground truth results. I don't know why they're kind of tricky to me a little bit. It's been a little while. I really think that we're going to be using the distributive property in some way. Oh, this is bothering me. Oh wait, AV equals 0. And we know that 0 equals 0V. That is a result that we know. That's like one of the theorems. And then if AV equals 0V, then A equals 0? Hmm. No. No. I think by cases, we can say, suppose if A is not 0, I mean, like case 0, if A is 0 and V equals 0, then there's nothing to do. We're done. Case 1, if A is not 0, then AV equals 0V How do I prove that the AV is the 0 vector? I mean, the definition of the 0 vector is some vector, and I guess it needs to be unique, such that a unique 0 vector, such that no matter, like if you add it to anything, you get the thing back. And we assume AV equals 0, so assuming AV is 0, we want to show A not 0 implies V is 0, and V not 0 implies A is 0. Case 1, A not 0, AV equals 0. I'm like repeating myself so much, it's starting to like sound like, okay, so what's going on for y'all? Oh, first year med student. All right. Like to study physics and math using books after high school. Cool. So far, truth tables are really getting me, but got to be rigorous, right? Yeah, truth tables. Yeah. Physics is fun. I haven't done any physics in a long time. I'd really like to work some physics problems again. Okay, so A naught 0. A naught 0 and AV is 0. Then we want to show V is 0. Well, what happens when we add V and AV? Is this a thing? Do we want to do this? 1 plus A times the vector V. And if A is... I don't like that. I do not like that. I don't think that's going to work. Oh wait, okay, so V plus AV take any other vector W, and we want to show that this still equals W. We don't know that any other vectors exist, right? The only vector that we know always exists is 0. Yeah. Hmm. Wait a minute. What about this? If AV equals 0, then AV plus 0 also equals 0. And then AV, since AV is 0, then we have AV plus AV equals 0. And then we have something like A times V plus V equals 0. Since A not 0, I feel like this is a circular argument right now. I'm about to say that since A is not 0, then V plus V has to be 0. And then V equals negative V. And the only factor well, no. What am I talking about, y'all? I didn't even do this right. This doesn't even make sense. That's not correct. That's not correct at all. Math is hard. It's kind of like we get to a contradiction here, but that's not... I don't think that that's accurate, because we can take the integers mod 2. We don't know that 2 exists as a separate element than 1. Here we got A is 0. But something's wrong, because this argument basically always shows that A is 0, and we wanted either A is 0 or V is 0. So something went wrong. I'm so confused. I'm so confused. I don't know why I'm struggling today. It's okay. It's been a while. It's been a while since proof-based mathematics, and especially ground truth algebraic arguments like this. Whew. All right. I've been very much into books from MIR publications, old Soviet textbooks. Ooh, interesting. I've never heard of those. Huh. Interesting. Cool. Okay. Well, It's just one of those days. Yeah, I know, it's fine. I'll pause, I'll just move on, come back later. Let's come back to so like when you get stuck on a hard problem and you can't make progress, go back to something easier and work on something easier and then come back to the harder one. Let's start the next section of Strang. What is the next, like, easy baby Strang is making us feel better about ourselves. Let's come back to it. What's section 4 about? Matrix multiplication. Ooh, yay, I've already done some examples of this. Matrix multiplication. All right, I feel confident that we're going to get some of these. A, B. I don't know what CR means, but I feel pretty good about A, B. How many problems do we have in 1.4? I'm not reading the sections here. I'm just jumping right to the problems and trying to remember. Trying to remember how this stuff goes as we move along. All right, so 20. We have 20 problems in this. 1, 2, 3. And this is all of chapter 1, too. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Let's get them all. Let's get them all. So 1.4. This one is bothering me. I want to do it next time. Let's fix that one. Or just look up the solution and just keep going. All right, Strang 1.4.1. Okay. Rewrite this four-way table for AB equals C. What the heck is a four-way table? When A is M by N and B is N by P. Interesting choices of letters. P. I think people usually use L. I don't know if that's... Yeah, I think I usually see L. How many dot products and columns and rows, what the heck, and rank 1 matrices go into AB? Interesting framing. And rank 1 go into AB. What the hell are you talking about? In all 4 cases, the total count of small multiplications is MNP. Huh. I don't... Okay, so when he says rewrite this four-way table, I think he's referring to a four-way table in the section, but what we're looking at is matrix A. It has M rows, N columns, m rows, n columns, matrix B. So if we write that more explicitly, A11, A M1, A M N, A1N, matrix B, he said, was N by P. I'm going to write B11 dot dot dot, BN1 dot dot dot, BNP dot dot dot, BN1, B1, 1P. Okay. Rank 1 matrices go into AB. That's weird, like the term small multiplications is really interesting. But this is going to equal this matrix C. Rows and columns multiply. So there are going to be M, M by P. For example, if A is a 2 by 3 matrix, 1, 2, 3, 4, 5, 6, and the next one is a 3 by 4 matrix, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Then the resulting matrix is going to be a 2 by 4 matrix. 2 rows with 4 columns. 1, 2, 2, 3, 4. 2, 3, 4. There's going to be those entries where each one is a dot product of a row from the first matrix and a column of the second matrix. How many dot products are there? It's going to be the number of rows from the first times the number of columns of the second. Yeah. Rank 1 matrices. I think by rank 1 matrices, he means like just single elements. So there are, literally M by P dot products and rank 1 matrices, I think. Let me check chat. Anybody here know what we're doing? Hey, how's it going, Atlin? Yeah. Or yeah, happy to stumble into a small group of hardworking mathematicians. Hell yeah. We're doing what we can. We're improving ourselves. We're studying. We're studying for fun. That's great. Thanks for joining us. Tell us about what problems you're working. Yeah, a lot of physics and math application in human physiology. Oh, there's a ton. All right, math spellbook. Yeah, I skipped a problem, worked on the next problem a little, and immediately came to the answer to the part of the last question I was struggling with. Yeah, I'm sure that I'm gonna immediately, or not immediately, but like later on, I'll like look at that problem again. And I'll be like, oh yeah, I see it now. Proofs are like that. Proofs, you need to step away sometimes and just try again later. Proofs are hard. So I've convinced myself that yes, there are M by P dot products and rank 1 matrices, I guess. And each one of those has n small multiplications. I don't know. Yeah. I think it's, I don't know. This isn't that interesting. I'm pretty confident that that's, I see what he's referring to in that. Strang 142. Let's keep going. Pretty sure I see what that one was intending to show. If all columns of A equals small matrix A, small matrix A, small matrix A, or no, small element A contain the same non-zero A, small a, what are C and R? Okay, I need to review the theory. What is the theory that we're talking about? C and R, like the rank of a matrix? Or, like, I feel like we're talking about blocks and, yeah, I need to read this section. Theory. So the first Nope.
Set the alarm for when?
Nope. No.
Okay, I won't.
All right. To multiply AB, we need row length Okay, so what he's saying here is we need the number of columns of A to match the number of rows of B. Yeah. The number in row I, column J of AB is row I of A, column J of B. Okay, so I'm going to say it this way. AB equals C, Cij equals the dot product of a row I what's a good way to write that? The ith row of A, this is sort of cheating, but like row I of A and column J of B, the dot product of those two. Like, I'm cheating by saying that the J here is referring to the column J. Like, I's are rows and J's are columns. I'm trying to get it in like a notation that's easier for me to visually remember and be able to write down quickly, as opposed to always writing out the full sentence that he wrote, which is like the ith row of A dot somehow that's just harder for me to remember than something like Cij equals AI dot product Bj. Something like that, somehow remembering that I is row, J is column. To me, in my mind, that says the same information, even though it's like not perfectly rigorously like you can't write that into a computer and for the computer to understand it. By columns, okay, A times column J of B produces column J of AB. Okay, so rewriting that, I can say A times Bj equals Cj, capital C, subscript J. That's cool. For AB does not equal BA. It says usually AB does not equal BA. But we do have associativity. A times BC equals AB times C. If A has, here we go, here's what I'm looking for, independent columns in C, then A equals CR. Like, what is this? R. If A has R, it says if A has R independent columns in C, That last part is really interesting. I don't know if I fully get it. Rowway dot products, column way, combine columns, rowway, column way, associativity, distributivity. Hmm. Oh, okay. Okay, I think I'm starting to get it a little bit better. Let me pull up chat. What's going on with y'all? How's it going? Yeah, alright. Nothing new. Alright, so Strang has this example of a rank 1 matrix. That's one example, but like in general, we're factoring AB equals CR or something. Oh no, A equals CR. He never really super clearly writes what C is. He starts defining it in terms of examples, I think. Well, no. It's just, yeah, that there is some matrix C that A is related to by independent columns in C, and then some other matrix exists, R. And he has this example. A is 1, looking at columns, 1, 3, 2, 2, 6, 4, 10, 30, 20, 100, 300, 200, and that can be written as 1, 3, 2 times 1, 2, 10, 100. So in this case, A is this big matrix, here's a matrix C, and here's a matrix R. And they both have this one linearly independent column. It has one independent column in C. So like lowercase r equals 1, and m by r by n is, in this case, 3 by 1, 1 by 4. 3 by 1 is right there, and 1 by 4 is right there, like 1 row and 4 columns. It's hard for me to see it immediately, but it is true that this times this gives you the other much bigger matrix. Like the first row times the first column is 1 times 1. The first row times the second column is 1 times 2. The first row times the first column is 10. Yeah, 1, 2, 10, 100. Second row times first column is 3, 6, 30, 300. 2 times 1, 2 times 2, 2 times 10, 2 times 100. So we get the large matrix with all of those numbers in it. Okay. So now if we come back to this problem here that we're looking at, if all columns of A equals A contain the same A naught 0, what are C and R? They all contain the same non-zero element A. We have some sort of factorization A equals CR. And we have m by r, lowercase r by n. On this side, A is 1 by 3, so we know since it's 3 identical numbers, they are certainly linearly dependent. They're rank 1. The matrix is rank 1. So R is 1. Then C is 1 by 1, and R is 1 by 3. Those are the sizes. And oh, yeah, and like they need to be identical. The columns of A need to also be linearly independent columns of B. So this is then the 1 by 1 matrix times, I think, 1, 1, 1. Yeah. I think that's it. Okay, I'm going to call this one done, but I'm also going to give it a yellow check mark. I want to come back to this one and repeat it because it took me a little bit of time. I don't know if I don't remember seeing this factorization CR before, so it's a cool problem. It's a cool problem. I think that was number 2, and we've already done number 1. I'm gonna do another 1, 4, 3 Strang. This stuff is cool. This stuff is great. I'm having fun with this entire stream. I think it's a cool, fun concept. And y'all can be studying alongside me, let's all just be positive pressure for each other to be working on our respective studies. I bet people have already dropped off. I bet a lot. Is the iPad still on screen? It is. Good. Okay, great. I wonder how many people are still watching. I have not been tracking the analytics. Oh, got to go. Thanks for the productive stream. Positive vibes, lights, energies, wishes, and unexpected wonders to all you guys. Take care. Yeah, I didn't see that until right now. I apologize. Oh, maybe you did just type that. Good to see you, dude. Thank you for stopping by. It is fun. Lots of positive energy to you as well. All right, cheers. I may have to take off somewhat in the nearish future, but this has been really fun for me. Bohnanza number 1. Linear algebra Bohnanza number 1. Cool. Let's get through this. Let's get through this problem, though. Let's take a look at one more. Yeah, this is an interesting factorization. I've forgotten about this kind of thing. Let's come back to the theory. It's an interesting theory. We've got this neat little algorithm, and we're saying C contains the first R independent C contains the first R independent columns of A. Suppose we go left to right. I'm not going to write it all out. Suppose we go from left to right looking for independent columns in any matrix A. If column 1 of A is not all 0, put it into matrix C. If column 2 of A is not a multiple of column 1, put into C. Yeah, so just keep going through and determine if the new column that you're checking is a linear combination of prior ones. Yeah. If column 3 is not a linear combination of col 1 and column 2, put into C. I mean, yeah, all we're just saying is like take the independent columns of A. At the end, C will have R columns taken from A. That number R is the rank of A and C. Um, so, yeah, neat. I mean, basically, we're just finding the kind of like sub matrix of A that is linearly independent column vectors. When A is 2, 4, 1, 6, 12, 3, 4, 8, 5, the space of linearly independent vectors is I think 2, 4, 1 and 4, 8, 5. Is that right? Yeah, that is right. Okay. Cool. I got it. And then the rank is R equal 2. Hmm. 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 Cool. Okay. Yeah, okay, so we're using the types of facts as like this column is equal to hmm well, I don't know. Yeah, linear combinations of columns. So like here this is 3 times column 1 plus 0 times column 2. Um, that equals that column. Yeah, I don't know. That interesting. Interesting. Been a while. Been a while. Yo, Jeffrey. How's it going, dude? Good to see you. This presentation is like this math section is different than how I learned all of this stuff. It's neat. Lang's book is cool. Okay, well, I'm just going to try to solve this problem anyways. Multiply A times B, 3 examples using dot products. Okay, you know what? I know how to do that. Good. I know dot products. This is the way that I learned it a long time ago. I can do this all day, y'all. 143 Strang. This is the easy way. We got this. So first we're going to do 1 0 0 1 1 0 1 1 1 times 143 1 0 0 negative 1 1 0 1 negative 1 1. I can do this. That's going to be 0. This one's 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 going to be 1. This one's going to be 0. 1 minus 1. Ah, okay. Almost. Yeah. 1, 0. This one is a 1 right there. So this is almost the identity matrix, right? But did I copy this down wrong? 1 minus 1, 1. Nope. Third row, dot product, first column, 1 minus 1, positive 1, is 1 minus 1 plus 1. So, yeah, we were very close to the identity matrix, but it's not. Okay, so that's part A. Part B. What is part B? Ooh, much smaller. 1, 2, 3. I love 1, 2, 3, 4, 5, 6. 4, 5, 6. So this is just going to be a 1 by 1 matrix. 4, 14, 32. Right? Okay, so 4 plus 10 is 14. 14 plus 18 is 32. Yeah. Cool. Part C. I wonder why he went to 4, 5, 6, 1, 2, 3 as opposed to 1, 2, 3, 4, 5, 6. But I think it'll all work out the same. This one is going to be a 3 by 3. First row times first column. First row times second column. First row times third column. Second row. Third row. 6, 12, 18. And that's it. Cool. One, 4, 4. We're going to check associativity. For these matrices, 1, 1, 1, 1, 1, 1, 1. Okay, so these are A, B, and C, and if we computed A times B, C, then this is going to be 1, 1 times, this is going to be a 2 by 3. First row, first column, first row, second column, first row, third column. But then if we multiplied it the other way around, AB times C, well, let's do it down here. Okay, so associativity worked for that one. We're going to see that it works for the others, just for good practice. 1, 2, 0, 1, 1, 3, 0, 1, and 1, 4, 0, 1. Okay, 2, 3, 4. How nice. One, 4, 7, 0, 1. One, 9, 0, 1. A, B, C is now going to be 1, 3, 4. This feels like a thing I've seen before. Upper triangular matrices have some cool properties. 3, 5, 0. Yeah, Yeah, there are great properties about these matrices, I think. I think. Four, 9, 0, 1. Yep. So they match. And now I think that's it for that problem. I think that we might be good for today. We've done a bonanza. We've done our first ever bonanza. I hope y'all are enjoying this stream. Hope y'all are having a good day. How long have we been live? 2.5 hours? But I took a long break in the middle, so maybe we should do more? I don't know. Should we? Let's take a break from these problems. And I literally just want to write out some Shilov. I just want to rote memorize for a second here. Let's turn off our brains for a second. Let's just copy out some math, some beautiful math from this more difficult book. Where were we? We had fields, got to determinants of order n, wrote them out. Geometric. It's got a nice little paragraph proof that the determinant it's the same determinant. Why is he just rewriting the same thing? Oh wait, 1 1. Oh wait. Yeah. Alright, so he just wrote out the transpose of the matrix by interchanging rows and columns with the same indices. This is a case where he says the terms obviously consist, that the terms obviously match in the transpose, in the determinant of the transpose. Not obvious to me, dude. Not obvious to me. I'm a knucklehead. I got a smooth brain. It's been too long. I don't see it. I just don't see it immediately. It's not that obvious. You jerk. Why is it obvious? I guess if A is this matrix and A transpose is... Oh, well, this was A transpose. But when you take any of those diagonals and you multiply them across, the transpose flips corresponding elements along that diagonal. It like flips that top right corner to the bottom left corner. Like, in a sense, the transpose kind of like flips everything over that diagonal. So if you flip everything over that diagonal, then every time that you take a product along one of these lines, then the product matches. And if you flip along that diagonal, then similarly that term is just going to move over to this other side of that diagonal when you subtract all of the negative terms. I can kind of see it, but it's not obvious. You jerk. You jerk. Go fuck yourself, Shilov. Not really. But still, rude. Therefore, it is enough Okay, well, if they have identical terms, then I think it's clear to me that they have identical signs, and that's because the... Well... Okay, well, I kind of follow the proof. Yeah, I think I get it. And I see that he is basically doing the same sort of analysis. Oh, my iPad's dead. But he's doing the same analysis that I was seeing, that you can see it, a rotation around that principal axis or a mirror around that principal axis. How do you, is it the same for a square? Yeah, I think for a square it's the same thing. And he's saying that he's doing the geometric proof of, or the geometric interpretation of the terms of a determinant, where you count the number of line segments that are like kind of going upward as opposed to downward. Like you look at the slope of a line segment connecting two terms of the determinant, and if the number is even or odd, determines the sign of the term. I don't know. Yeah, it's just kind of like, it's a gnarly proof, I feel. It's not obvious at all. The dude is rude. The dude is rude to me right now, but I think I follow the proof. It's just, yeah, it's a lot. All right, well, thank you, everybody. This was a hardcore bonanza today. I had fun. It was fun. I don't know. I doubt anybody ever is going to watch the entire video, but thank you if anybody does see this. 4 hours, that's cool. Was it 4 hours? That's intense. That's a lot of time. Dang. All right, well, thanks. This was super fun for me. It's cool to be doing some math again. Have an awesome day. Cheers, everybody. Happy mathing, and yeah, enjoy your day, enjoy your weekend. Bye. Thanks for watching. Bye.